Hi everyone, those who don't know me, I'm Hugh Sanderson, responsible for the C++ target. Today's talk I've called A Day at the Seaside, which is a slight variation from the working title of dribbling on about hxcpp, which doesn't have as good imagery as the seaside. So this is actually a picture of Rottnest, which is like a holiday island just 10 kilometres off the West Australian coast. It actually has a tie to Amsterdam that I can talk about a bit later. So some highlights for the last year, or since the last Haxe conference. I've done some work on native integration. There's some garbage collection improvements. The sepia has moved over to use the same internal representation of the AST as the CPP code did last year. I've added just-in-time compiling to sepia, and finally added some documentation. So this little guy is a native of Rottnest. The Dutch explorer Vlaming called the island thinking it was a giant rat, whereas in fact it's a small kangaroo. But you know, can't blame him for that. So the native integration has progressed with iOS. Now you can use the Obj-C define to enable full iOS or Objective-C integration mode. This means that you'll generate .mm files instead of .cpp files. .mm file can call both C++ and Objective-C code, so that's quite handy. You can tag external classes with the Obj-C metadata, and this means that when the code goes to call functions of those classes, it'll use the square bracket object message notation instead of the C++ call, which means you can call directly into iOS operating system calls. This is contribution from Kawe, who's not here this week, and also got some sponsorship from Pucker Pets, who were interested in a watch app. So the iOS integration, there's a pretty easy correspondence from the iOS types to the Haxe types, NSData, Haxe.io bytes, dictionary, dynamic. Now, as long as the dictionary contains sort of these types listed here, it should be fine. Strings, obviously. The object wrapper is a bit tricky because if you want to store a Haxe object inside Objective-C, it's going to want to take a reference count on it, and the native Haxe objects don't support reference counting, so it creates a little delegate object and passes that off to the Objective-C where it can hold onto it, and it's got a little garbage collector root, so it keeps ownership correctly. Objective-C blocks, which is the kind of new style callbacks that iOS uses, sort of equivalent to the anonymous functions in Haxe. So you can actually pass a Haxe function with a correct signature to one of these Objective-C functions that takes a block code, and it should just work. The protocols, how Objective-C groups functions together. With Haxe, it's equivalent as an interface, and in fact you can implement an Objective-C protocol and have that work, pass yourself off as an object to one of these iOS functions, and it should call back into your functions correctly, including some correct type conversions. It's a little bit tricky with the protocol because often the iOS functions will take a weak reference to the protocol because they use reference counting instead of a proper garbage collector, and this is a little sort of hack they use to avoid circular references. It's problematic because when I pass a protocol off, I create a little delegate, and if you pass that off, it'll actually be the only thing they're holding on to that delegate will be the callback, and so it'll reference count itself down to 0 and disappear with a weak reference count. So you have to do a little bit of a hack to make sure you contain an extra reference on this protocol. The easiest is to store it in a static variable. I've also added nslog, nserror helpers, so you can call nslog directly with your Haxe strings. So this is a little example of a iOS extern. You can see it's just the UI image class. It's got the Obj-C metadata so that it knows it will use the square bracket notation to call it. The include file, so if you ever use this extern class, it will automatically include that in your C++ generated code. And you can see it's a fairly natural way to write an extern. Having got the UI image, you can then pass it off to any of the other API functions. Probably not store it in a member function without having to think about how you're going to reference count it. But that's kind of another story. Like if you actually want to start storing these things, you have to think a bit more about it rather than just keep them on the stack. There's a little example of a watch app running directly. This is an hxcpp app, but it has no runtime associated with it. So there's no NME or anything running, making operating system calls. It just makes the operating system calls directly and receives callbacks into the Haxe code to, on frame ready or animation or however the API goes. So there's been some more C++ integration too. I put this CPP star thing in to kind of replace CPP pointer. It's not quite a replacement. It doesn't have the kind of indexing that the pointer has. But if you need to type up an extern that is, you write int star x, that would be a CPP star to int. It's a more accurate way of typing the extern, and I'm trying to move towards it. There are still some things in the standard API that use pointer instead of star, and I'll probably look to change those over, or at least make them work both ways. So it puts the natural C++ pointer in your class. So if you look at the source code, you'll have int star x in there. This used to be an issue with dynamic because if you try to convert an int star to a dynamic, it would go through the bool conversion and you end up with true or false, which is not really what you want. But now I've instrumented the Haxe code so that it'll stick these automatic conversions in and actually convert from do the convert from the star to the pointer wrapper so that you can pass it through dynamic and then get it out the other end. If you're using the CPP header files directly, they're the atomic exchange if pointer is a way of doing some lock-free algorithms. I use that internally, so that's now supported on the platforms supported by CPP. And I've added some IPv6 internet support. It's not 100% because the Haxe API itself is not really fully upgraded yet. But if you create a host with an IPv6 name, it'll create the host class, which you can then use in your sockets. And it seems to be working reasonably well at this stage. So Toolchains, been some work done on the Toolchains. The Mac Toolchain has an upgraded deployment target now. 10.9 if you use some of the C++11 stuff. It's not really a problem because Apple doesn't really care about keeping the older Macs going, so I don't think anyone's going to have too much of a problem with this. The watchOS toolchain that we saw earlier, that's been added. It's pretty similar to the iOS TV ones, just some slightly different flags. The NVCC toolchain, this is the CUDA compiler for NVIDIA GPU acceleration. This integrates now with the CPP build tool. You obviously have to have the SDK and stuff installed, but you can use that quite easily now. I've used this to compile the TensorFlow library using the CPP build system. And MSVC 2017, it's there, it's ongoing. Microsoft, in their wisdom, decided to move away from the simple environment variable to tell you where their SDK was installed, because that's just way too under-engineered. Now you can download an executable and get the output of this directory in XML or JSON format. So it's a much better solution now going forwards, but it does mess a little bit with the way we try to have a minimal way of auto detecting the system. I think it's not working for anything other than English at the moment. Which actually brings me to some things that reminds you why I like Haxe. Just looking at the download side, Haxe is we call it a toolkit, and I think it is really a nice little thing that almost everyone could have installed on his or her computer. It comes in at 5 megs, and it gives you the ability to write a little command line Nico app, everything you need. Then you can add hxcpp to this, and it gives you the ability to build a sepia app, or run, if you've got Linux and you've got your compilers already installed, build a fully fledged desktop app, and that's just a little bit bigger. Bigger again, you can add NME to bring in your graphics library, so you can have full graphics application running on Linux. This is Miniming, which is an old library that I've got in the system, and this is a full GCC toolchain for Windows, which I stripped out all the stuff you don't really need. So it's just got the compilers and the linkers and some header files. But you can use that as a library to compile your C++ code on Windows. So all those together, you can write a fully native Windows graphics app. And then compare this to Python on Windows, which comes in at almost 100 times the size of Haxe. It's obviously got a lot of batteries included, but obviously you're not going to be using them all. So it's getting more sort of enterprisey and sort of becoming a real bit of a barrier to just getting started quickly, I think. But it doesn't really compare to Android Studio now, which is up to 2 gigs, for you, and more. Yeah, it gives you. I mean, it's got an IDE Java compiler, but if all you want to do is sign an exe, having two gigs seems a little bit excessive. But it's still less than Xcode. It comes in at 5 gigs. I mean, to be fair, it does have several different architectures that it can output and a bunch of other stuff. But you probably need to upgrade macOS as well, which is another, 4 or 5 gigs. But now, Microsoft have done one better, and they come in at 10,000 megs, which 2,000 times the size of Haxe. So it really makes me think that these guys should all be shipping Haxe as it's just a small fraction of their additional overhead, and give everyone else a chance to use a great language instead of the ones that they're peddling. So work on the garbage collector. Any work on the garbage collector, I think, is good because it actually affects all applications. So some general things I've done in this area, I've combined quite a few of the thread local data, which is sort of context you have for each thread that's running. There's debug, there's the sepia stack, there's the allocator, there's also telemetry and profiling information. Now this is all combined into a single structure, and I can grab a pointer to this structure as I enter a function, which means I don't have to do this thread local operation, which is a little bit expensive, not too expensive, but certainly better avoided. And I don't need to do that every allocation. I can do it once per function that uses an allocator. So that saves a bit of time. I've added recycling of large objects. So if you create an array, let's say 1,000, I would say 1 million elements, and then you push another element on, I increase the array size, but I don't increase it by 1, I increase it by 50%. This is a compromise between having to increase it too many times and having too much extra space that you're not using. But now what I do is, having decided on the array size, I then round it up to one of a predefined set of sizes, which means that the arrays come in at a certain size, and there's only several different sizes of arrays that you can use, which then means I can use object pools efficiently to manage these large objects. It's surprisingly how slow it is to allocate like a megabyte on an Android device. So this really helps. Now the pool's quite dynamic and quite small. It only exists for the one collection cycle. If they're not used by that, it just recycles them straight away, because there can actually be quite a bit of memory tied up in those arrays. I've also put in lock-free data structures. So when CPP went to grab a new bit of data to use for allocating into, it used to involve a lock, like a system lock, and they can get expensive. They're not terribly expensive, but if you're doing thousands of them, it adds up. So now that's the lock-free, does some spin locks and some things like that to try to avoid doing that. And I've moved more objects to non-garbage collected memory. So when it starts up, the class data, which is list of the fields in each class and their parent class and things, they're all constant and they're not going to change. So I've moved those into normal memory. So when it has to do a GC mark, it doesn't have to traverse these objects because they're constant. And this means that by the time it gets to actually run your application, it's really only done a handful of sort of GC allocations. So it should improve the trace time quite a bit, well, at least a bit on every application. So I guess the big change to the garbage collector is adding a generational phase. The generational hypothesis is that it's better to burn out than fade away, and that all the objects will die young. Now, this is not strictly true, but where it is true, you can get an advantage. What happens is, keep track of all the objects that have survived the last garbage collection, and when we create a new object, we create it in a different area, and we only care about if we store a reference to that new object from an old object, and in this case, we have to record the fact that this old object has a reference to a new object. And so when we come to do the garbage collection trace, we only need to trace a few of the old objects, the ones that actually point to something that we care about, because all the other ones we assume are just pointing to themselves. And this can really speed up this fast garbage collection phase, but we still need to do a slow one occasionally, because this neglects the fact that old objects may no longer point to other old objects. And if that's the case, we should be freeing these old objects. But in a generational collection, we only ever keep stuff. We don't actually release stuff. So it still needs to do the occasional slow collection. And depending on the algorithm, it might need to do slow collections every time. Another issue with generational collection is that as we write a new object into an old object, we need to remember that we've done that. And this means that I need to insert code everywhere that we write pointers to make sure that if we're writing them into an old object, that we remember that fact. So that adds a little bit of runtime overhead. But the theory is that the overhead you get is saved by the time it takes to do a garbage collection later. Now, I also delay some of the bookkeeping. When I create an allocation, I keep track of whereabouts a few things are, and I can avoid doing that until I've actually decided that I keep the object now, and that saves a little bit of time in the allocation as well. The CPP generational collector is a non-moving one. Traditionally, these old and new objects are separated by some kind of memory address boundary, either bitwise or just a threshold. Because I already had all the information required that each object itself can either be one or the other, it doesn't really matter. It means that I don't have to do a moving phase in the collection, which speeds it up, but it does mean that the write barrier is slightly more complicated. So not sure what's exactly the best there, but this is the simplest and it's working, so I'm sort of going with that. A trick too is that if you have external code that's writing into object pointers, you do need to know whether or not it's doing a generational write or not. Generally, it's not a problem. Like if you're using CFFI, the API hides the fact that you're writing the pointer entirely from you, so you shouldn't have any issues. It's only if you're going to go object arrow parent equals something. If the parent is new and the object is old, it's possible that you'll lose that reference to the parent under some circumstances. So hxcpp generates these underbar set functions that you can call directly if you're doing that. Don't imagine anyone will be, but that's something to keep in mind. The other option is to not turn on the generational garbage collector globally for your library. As I mentioned, the performance is not guaranteed. It's supposed to be, well, it is better on average, but in some places it can be not much difference at all, and then you've got a write barrier to contend with. And the full collection still takes as long. So your worst case pause time is still going to be as long, which, I mean, if you're in something like a game, it would manifest as a stutter. It doesn't really solve that. It will decrease the frequency of the stutter, but not eliminate the duration of it. So if you want to try some of these options, there's the defined GC generational, which actually enables it for the whole app. This GC summary is pretty good. You might want to put that on in your CPP non-release apps just by default. What it does is when the program terminates, it just prints a little report saying the percentage of the time spent doing garbage collector. And if it's much more than 10%, then maybe have a think about sort of why that is. This dynamic size is an interesting one. Normally, CPP would use some scratch space to allocate into, and once that fills up, it does a collection. And it has a heuristic where it will use 20 megabytes or the size of the data that the program's using. So if your program's using 100 megs, it says, well, 100 megs constant, 100 megs that I'll use for scratch space, and proceeds from there. But in some cases, you might want more scratch space because if you can delay the GC call, then you have fewer calls, and fewer calls means less time spent in the GC, assuming each one is about the same length. So on the flip side, though, you don't want to be allocating too much memory, because sometimes the cache can make that slower, and other times also you just are, you're not being good citizen on your device. So there's two options. One is you can actually explicitly set the amount of scratch space in your app. So you can just say, I want 400 megs of scratch space using the Haxe API. Or the other one is this define will allow it to use up to 5 times more scratch space as it does normally. It monitors the amount of time spent in the garbage collection and increases the space if it thinks it's going to get some advantage from doing that. All right, so Sepia, there's been a bit of work done here as well. As I mentioned earlier, it now shares the internal representation AST with the CPP code, which is stronger typing. I got a little bit lax and just said if I can't work it out, I just made some stuff dynamic, but now it's not. It's all strongly typed, so it should be faster. It's got just-in-time compiling, so which is enabled with the JIT command line argument. x86, 64, ARM32, and ARM64 covers the platforms that CPP does. You can turn it off if you're doing Sepia, for instance, on an iOS or maybe UWP App Store app, but you're probably better off compiling with CPP anyhow if you've got to that stage. The implementation is fairly naive, doesn't really look to eliminate temporary variables, it just starts from one end and goes to the other. So there is possibility of some improvements down the line if you want to get into some of those more interesting problems. So lies, damn lies, and benchmarks. If we recall 2016, last Haxe conference, the Mandelbrot set, which is a very heavy garbage collection application. In fact, it doesn't retain very much at all, so it's really just measuring the time of calling alloc. CPP had some improvements to get to 1.92. JavaScript was still comfortably in front of it at 1.1 seconds. Java looking pretty good at 0.76, and Sepia was off the scale. But now the CPP comes down to 1.2. This is using the micro optimizations by moving some of the TLS code into a common area, lock-free allocations, and delaying some of the house bookkeeping, which is on par with JavaScript. Now here the JavaScript is the same result I had last year. I haven't upgraded my little node tester. I think that's why it hasn't improved. I suspect it would be better than this if we were to use this current year's version of Node, or even the Microsoft JavaScript engine is looking pretty good as well. So I might be doing JavaScript a little disservice there. If we look at the generational GC to CPP, and it comes down to be comfortably below the JavaScript now at 0.91, which is sort of twice as fast as it was in last year. Java has had some improvement. I did upgrade the runtime there, so that's come down a bit on its own, which is still looking pretty good. The next one is not really a fair comparison. I'm just showing that if you wanted to use 2 threads with C++, you could, and get it down to 0.51. But yeah, that's not really a fair comparison there. That's just as an aside. And you can see now with Sepia JIT, it's at least on the chart, 3.1, not too bad. It's still quite a gap to JavaScript. Obviously, they're pretty much doing the same thing. JavaScript's just doing it better. I think I could probably narrow the gap, but I don't think I'll ever close it. So I think it's still worth pursuing a little bit because Sepia has some other advantages in like the runtime size and using it on top of an existing CPP program. Another benchmark, the Splay test, which is from the Java benchmarks. So I'd expect them to do well because they would have tuned for it. It's characterized by slow GC churn, which violates the garbage collection hypothesis of dying young, and therefore you don't really get any benefits from it. But I did notice that the JavaScript was using 400 megs of scratch space, where CPP was using 20. So I've added this dynamic size, and which increases the size to something like 200 megs. So it's certainly in the same order of magnitude as the JavaScript for a fair comparison. And you can see the JavaScript CPP without the size coming in at 505 microseconds, JS faster at 434, but now with the dynamic sizing increasing the scratch space, CPP comes in faster again. Java here is having some problems. I think it's to do with the way the test generates garbage. It's a combination of arrays and anonymous objects, and I think it's actually probably some overhead introduced by the Haxe Java for reflection or something that's causing an issue there. And CPJIT is also not doing too bad here, coming in only twice as slow as CPP, and hopefully get that down a little bit with some register optimization if we want to go in that direction. So the ubiquitous BunnyMark, here bigger is better instead of smaller, using a fairly decent graphics card, GTX 1060. CPP comes in at 600 kilobunnies. Sepia now can outperform the JavaScript. Now, maybe this is not a fair comparison for JavaScript because this is using code I wrote for the JavaScript, and maybe someone can do better there. But I think the point is that because the Sepia here is using a combination of C++ and Sepia scripting, some of the work is getting done in Sepia, like the controlling of things, but the rendering and stuff is getting done, and the display list is getting done by C++. So it's kind of a hybrid model, and I think this is where maybe Sepia might have a bit more of a niche. And interesting too that the Edge browser is doing better than the Chrome browser in this particular case, and so there's competition there is hotting up a bit. So documentation. This is a picture of a plate actually left by another Dutch explorer, Dirk Hartog, 401 years ago. Sailed from Amsterdam, came to Western Australia, didn't have notepaper with him, so he used a plate and wrote, I don't know, I think it says, tell Hugh to write more documentation, something like that. So the documentation now is in the hxcpp GitHub docs. There's notes on the compiler cache, threads and stacks, using build.xml, the defines and XML injection. I'll be talking about these this afternoon if you want to come to the talk with questions. There's also some work I've started in the Haxe manual, which will be on the standard Haxe website. This is more reference material and it's not in there yet, but we're looking to combine those together so that the Haxe manual becomes a definitive source for this stuff as well. So some miscellaneous. This is the most miscellaneous creature in the world, the platypus. It's got the bill of a duck, feet of a mole, tail of a beaver. It's a mammal and it lays eggs. So it's really a bit of everything in there. So now I cleaned up the output a little bit. So unless you actually put the debugger define on, it doesn't generate some of these macros that I was using with the debugger, which just makes the code easier to read. hxcpp is not shipping static or dynamic libraries anymore. Since last Haxe conference, they haven't been needed because it links the object code directly into the executable. And now they were taking up space, so I just got rid of them. I am, however, shipping some Sepia hosts for Windows, Mac and Linux, which means that if you create a Sepia file like you would a Nico file, you can run it with hxlibrun and hxcpp, the name of your Sepia file, with the -JIT argument if you want to test the performance. I also abandoned JS Prime, which was an initiative I was looking at to be able to use the CFFI on Java. But the problem is that if you use it in a browser, Java doesn't have any way of calling a finalizer. So you'd have no option but to leak resources if you were to use it naively. So I just sort of stopped doing it. So scorecard. How did I do from from my promises from last year. GC generational and concurrent, 50%. I got the generational, concurrent, maybe not so much. Refactored sepia and JIT, yep, they actually did happen. So it's not a bad score, I'm thinking. So what does the future hold for us beautiful Haxe developers? I would like to extend to GC concurrent from GC generational. GC concurrent runs the collection while your code is still making changes. And the real goal here is to reduce the pause time. So when you, if your game is stuttering, it's possible to reduce that time to a sort of bare minimum by doing most of the work before we actually get into this stop the world phase. The work done on the generational write barrier is a good start and should help me here. So it's not as a bigger task as sort of might have been initially. I also plan to turn the CPP string into an object. At the moment, it's its own kind of little special thing, but it involves, if I need to pass it as an object, I need to box it. But if I make it an object to start with, some of these issues go away, and this will let me do proper Unicode character indexing, which is not really not great at CPP at the moment. But it will mean that you can no longer use the underbar S native way of accessing the character data natively, which is maybe not a bad thing. It'll be replaced with something like UTF-8 str or CStr or something. There'll be a way of doing it. It just won't be using the member directly. There is the CPP native string class. I will just update that to refer to the new way of doing things. So if you use that instead of underbar S directly, you should still be all better. So int64 at the moment, it has a few little issues. If you stick it in an array, it boxes it, and Sepia also boxes it. So just to bring that into sort of mainstream fast as processing. Same with some structs actually. If you put structs in arrays at the moment, they get boxed, but to just avoid that boxing if possible. And then adding some lower cost debugging options. So at the moment, it's all kind of instrumented with C++ code. To maybe use some native stack walking code if possible, or with the combined thread local storage stuff I've got now, there are a few more little options of doing just a little bit of work in the function to get a proper stack, but without really slowing your application down. So sort of bringing that into being more of a default way, I think is probably a good way of going. All right, that's it. So that's what's happened this year. Any questions? Yeah, so Sepia is a bytecode language. So it compiles, if you use it like you would CPP from Haxe, you Haxe compile minus Sepia and then give it a name. It's like Nico, so it generates a .sepia file, which is just like the .nico file. The difference is that the thing that runs Sepia code actually is a Haxe program. So you compile your Haxe program, which can export all its functions to your Sepia code, and then the Sepia code, it's like scripts on top of it, but very tightly bound. So if you the Sepia hosts I ship just have the standard, regex and sort of standard functions in it, but so they will be able to run a command line that pretty well. You don't need to build your own host. But for NME, for example, I build my own host, put all the graphics calls in the C++ code, and then the Sepia can just script on top of those, so it doesn't need to do the full work itself.
As Hashlink matures as a target, do you anticipate, from a community perspective, that it'll be able to leverage a lot of the work done to bring CPPIA and hxcpp to its further targets?
Maybe you'll have to ask Nicholas that, but there is some things, like I've spoken to him, like the reason I can do these 4 JIT targets is that I've just found this external library on the internet that does it for me. So I'll talk to Nicholas, maybe we can join that in together. I mean, there is a lot of overlap, but I guess sort of fundamentally different approaches because I've sort of tied it closer to the C++ target. But there's certainly ideas can be shared, and stuff where possible we sort of talk about some of these things. Yeah. Any questions? Nope. All right, thank you.